Welcome to Mikab Model College online tutorial. We hope at the end of this lesson, you will have acquired the expected learning outcome. Sit down and listen attentively as we introduce your subject teacher.
Welcome to chemistry class. I am Saliu Abdulwahab, your chemistry teacher. In this lesson, we want to look at the relative atomic masses of isotopic elements. We have established the fact that isotopes do exist. And if isotopes do exist, what are the impacts of isotopes on the relative atomic masses of some elements? And we said that the impact is that it makes the relative atomic masses of those elements that exhibit it to appear in fractions or in decimals. Now let us quickly look at the atomic mass of an element is determined using the mass spectrometer. Atoms of the same element may have different masses, just as we have established in the modification of the Dalton's atomic theory. When they exist like this, the elements that exist in these forms are known as isotopes, and the process, the phenomenon in which they exist, is known as isotopy. In the case of the existence of isotopy, the following methods can be used to calculate the atomic mass of such an element. 1. We have relative abundances in ratio. That is, we can use the ratio method to calculate the relative atomic mass of such an element. 2. We can use the percentage abundances. The percentage abundances will tell us how more are they, which is more and which is less, which of the isotope is more and which of the isotope is less naturally. On this note, let us quickly look at this question and use the two methods to solve the problem. Chlorine exists in two isotopic forms, which are chlorine 35 and chlorine 37. If their percentage abundance are 75% and 25% respectively, determine the atomic mass of chlorine. Chlorine. Mass number 35, mass number 37. This 35 contributes to the atomic mass. This 37 also contributes to the atomic mass. However, since the number of protons or the atomic number are the same, we can excuse both of them in the solution to this problem. As a way of solution, let us bring back the isotopes, chlorine 35 and chlorine 37. Percentage abundance for chlorine 35, the percentage abundance is 75%. And for chlorine 37, the percentage abundance is 25%. To get the ratio of the percentages now, we divide the two percentages by the lowest percentage. From the two percentages, which is the lowest? Of course, 25% is the lowest. So 75 divided by 25 will give us 3. 25 divided by 25 will give us 1. Which means that the percentage ratio now is in ratio 3 to ratio 1. To have the sum of the two ratios now, we have 3 plus 1, which is equal to 4. And 4 is the total ratio of the two isotopes. 4 is the total ratio of the two isotopes. This means that 3 atoms of chlorine has mass of 35 and 1 atom of chlorine has a mass of 37 from their percentage ratios. Therefore, the contribution of each of the isotopes now will now be the isotope with percentage ratio 3, which is chlorine 35, multiplied by the mass number 35. That gives us 105. 105. Then the isotope with percentage ratio 1 multiplied by the mass number 37, 1 multiplied by 37, which gives us 37. Sum up the two results we have for the two isotopes, that is 105 plus 37. That will give us a total of 142. 142. The atomic mass of chlorine, therefore, will now be the average of the masses that we have. What is the mass? 142 divided by the total ratio, which is 4. 142 divided by 4 gives us 35.5. Therefore, the relative atomic mass of chlorine atom is 35.5. Now you will see that elements with isotopic forms do not exist as whole numbers in terms of their relative atomic masses. This same problem can alternatively be solved using this method again. Since 3 atoms of chlorine has mass of 35 and 1 atom of chlorine has mass of 37, that is chlorine 35 and chlorine 37, we can say that the percentage ratio multiplied by the atomic mass to give us 3 multiplied by 35 all over 3. And what is that 3? That is the percentage ratio. Again, percentage ratio 3 multiplied by 35 mass number divided by the percentage ratio 3 plus percentage ratio 1 multiplied by the atomic mass 37 divided by the percentage ratio 1. 3 multiplied by 35 plus 1 multiplied by 37 all over the total ratio 3 plus 1, which is what? 4. 3 times 35 will give us 105, 105, plus 1 multiplied by 37, which gives us 37. 105 plus 37 will give us 142, 142. And looking at the total percentage value now, or ratio, it is 4. Then 142 divided by 4 to give us 35.5, which is still the same result we obtained using the first method. Of course, we have established now that the relative atomic mass of chlorine is 35.5. Alternatively again, we can decide to use the percentage method direct without finding the ratio. And using the percentage method without finding the ratio, since the percentage abundance of the first isotope that's chlorine-35 is 75. And the second is 25, which is chlorine-37, is 25%. Now, let us look at how we can solve them. We are going to say, all right, percentage abundance of the first isotope, 75, multiplied by the atomic mass of the first isotope, 35. 75 times 35 will give us 2,165. 2165. The second isotope will be percentage abundance of the second isotope, 25, multiplied by the atomic mass of the second isotope, 37. 25 times 37 gives us 965. 965. Sum up the two masses that we have. 2165 plus 965, which gives us a total of 3550, 3550. But then the summation of the two percentages, 75 and 25, will give us 100%. Therefore, the relative atomic mass of chlorine will now be equal to the average of the two isotopes, which is 3,555 divided by the total percentage abundance, 100. This gives us 35.5. You can also find solution to this problem by using this method again, still on the percentage abundance. Because all right, the percentage abundance of the first isotope multiplied by the atomic mass enclosed in a bracket plus the percentage abundance of the second isotope multiplied by its atomic mass also enclosed in a bracket divided by the summation of the percentage abundances, which gives us 2625, 2625 plus 925, 925 divided by 100, which is equal to 3,550, 3550, 3,550 divided by 100, which gives us 35.5. Any of this method is preferred, just as you will deem fit. In conclusion, the atomic masses of some elements are not whole number. This is due to the existence of isotopy. Remember that you can apply this method to any element at all, based on the parameters or data you are given. Please do not forget to subscribe to this channel, because from this channel you shall be learning a lot of calculations in isotopes.